In this screencast, we are going to work through a pipe flow example problem in which the pipe diameter is unknown and thus the solution will require an iterative or numerical method type approach. We have a new water piping system that's being designed for an apartment complex. Now the supply of water to this complex must provide 1,200 gallons per minute at a pressure of 25 pounds per square inch. And this will come from a large diameter main city supply line which is maintained at 65 psi. We want to determine the appropriate pipe diameter to connect the city line to the apartment complex line. So we're going to use a plastic material for our pipe that's known to have an equivalent roughness of 5 times 10 to the minus 7 feet. We also know that we're going to use 100 feet of pipe, 4 threaded 90-degree elbows, 10 threaded unions, and a swing check valve for forward flow. So the elevation difference between the main source and the apartment source is 10 feet. We need to determine the pipe diameter to use. So when we look at solving pipe flow problems, we know to start with an energy balance that looks like the following. Now I've provided this in a certain form. You may see it in other forms, but you should quickly realize that if we need to solve for the diameter d, well, this isn't going to be a straightforward plug and chug type problem. There's a couple different terms that rely on the diameter, such as the velocity. Here's a diameter. The friction factor will be a function of the diameter. And then we have these other velocity terms. So we're going to need a computer solver or iterative approach to help us get our answer. So let's work through setting up the iterative approach, and then at the end of the video I'll show you using a computer solver to make your life easier. Now the first thing I like doing is writing down what we know and drawing our system. So a quick drawing just to give us an idea. I'm going to call this point 1, which is our source. And then we have a line, and we know we have 4 elbows. So 1 turn, 2 turns, 3 turns, 4 turns. And this is going to go to our point 2, which is our apartment complex source. So we know the pressures here, and we know the length of pipe. We also know that there is some connections in between and some kind of valve. So I'll just put a star there to represent our valve. So we're given the flow rate of 1,200 gallons per minute. I'll go ahead and convert this to feet cubed per second. And when I do this, I get 2.674 feet cubed per second. I like to change all my units as I start writing this out to one base set. So we know pressure at P1, our city source, to be 65 psi. Again, instantly converting this, I get 9,360 pounds per foot squared. Our pressure at our apartment complex needs to be 25 psi, which converted gives me 3,600 pounds per foot squared. We know the equivalent roughness of our pipe. It was told to us that it was 5 times 10 to the minus 7 feet. We have a length of pipe that's 100 feet. We also have, for our minor losses, 4 times a threaded 90-degree bend. We have 10 threaded unions, and we have a swing check valve in the forward position. So again, I'm using these to help us look up loss coefficients. So I'm going to go ahead and just look up the loss coefficients associated with these so that I could write them down. And for our threaded 90-degree bends, one table I have uses a loss coefficient of 1.5. For our threaded unions, I get 0.08. And for a swing check valve, I get 2. And this all comes from a fluid mechanics textbook. You could look these up probably in other handbooks as well. So again, I could save myself the trouble now. I could just do the math, and I could see that the sum of these loss coefficients is equal to 8.8. Now, based on the problem statement, we're not given anything else. But looking at the energy balance here, we know we need a density of our fluid. We're also going to need the viscosity of the fluid to get a Reynolds number down the road. So let's assume a temperature, and 60 degrees Fahrenheit is not a bad assumption for the temperature of city water. So the density, if we look this up in a table, is going to be 1.94 slugs per foot cubed. The viscosity at 60 degrees Fahrenheit is 2.34 times 10 to the minus 5 pound second per foot squared. And lastly, just to be safe, we'll write gravity down, 32.174 feet per second squared. We're missing anything? We are. We're missing our elevation. So we know that Z2 minus Z1 is equal to 10 feet. All right, so let's start with our energy balance and start simplifying it down. So we know P1 minus P2, since we have P1 and P2. Z1, Z2 we have reported as 10 feet. We have our density and our gravity. We have our length. And we have the sum of our minor loss coefficients. So what we're down to is looking for velocities as well as a diameter and a friction factor. Now what you might notice is that we don't have our kinetic energy parameter alpha in our equations. Now we're going to assume turbulent flow in this problem since we have a flow rate of 1,200 gallons per minute. So I just used alpha equals 1 and didn't even have it in our equation. We have three unknown terms, all involving velocity or diameter. And our kinetic term has two different velocities. Let's simplify this down to the easiest form to work with, which for me, I'm going to start plugging these values in, and I'll get down to the following. So I have my energy balance on the left side of this purple line. I've just broken it up into each individual component, and I've put the values in that I know on the right side. So one thing that we could easily get stuck on at this point is trying to figure out what velocities we're looking for. Now when we think of this system, water's coming from a main water line into one we are building for the apartment complex, and eventually out of some type of faucet in the building. So the specified large diameter of the supply line is there to give us the impression that the velocity in the main line is much smaller than that in the line we are building. And so for the sake of the problem, we assume that the velocity in the city line, V1, is negligible. So V1 is much smaller than V2. So now all the velocities in our problem are V2, which is just the velocity through our pipe network since the diameter is constant. So now we have one unknown velocity, V2, which shows up in 3 of the 5 terms. We have one unknown diameter, and we have one unknown friction factor. So the velocity is going to be solved by using the relationship that volumetric flow, which we represent by Q, is divided by the cross-sectional area of pipe A, which gives us an average fluid velocity V. So now we have our velocity as a function of D, so we can plug that into our other equation since we know Q, and now we're down to two unknowns, F and D. Here we're going to plug our velocity expression into this term as well as this term and this term. I've simplified a little bit, pulling out the D to the 4th, and I've plugged in the known values we had before, making sure all our units matched up. And when we do that, we get the following expression. So we have two unknowns, the friction factor F and the diameter D. Now unfortunately, the friction factor is not so easy. There are two ways to approach this. One is the Moody diagram. Based on D, we could solve for V, thus solve for the Reynolds number, calculate E over D, and then get F. So this is a trial and error iterative approach because it's all based on D. So we have to guess a D, get F, and then make sure that this equation is satisfied. The other approach we'll talk about in a second after we do this guess and check system. So let's write out our expressions. We have this one, equation 1, which is a function of F and D. We have the Reynolds number, which we need for the Moody diagram, which is rho VD over mu. And since we only want to work in terms of diameter, we're going to plug in this expression up here for our velocity. And when we do that, we get rho over mu times 4q over pi times 1 over d. Now we could simplify this since we know rho, mu, and q and get the following expression for the Reynolds number. Lastly, we have epsilon over d. And epsilon in the problem statement was given to us. Let's guess a D. A reasonable diameter for a pipe might be a 3-inch line. So our first iteration, we're going to guess 0.25 feet. So when we do that, right away, one check we can make is to plug that into our energy equation up here. So if we plug in a diameter of 0.25 feet, you'll find that the only solution for F is that it's negative. And we're not going to get a negative F from the Moody diagram. So right now we know that 0.25 feet is not possible. Let's try a diameter that's larger. So when we use 0.4 feet, I get a Reynolds number of 7.06 times 10 to the 5th, epsilon over d of 1.25 times 10 to the negative 6. This gives me a friction factor of about 0.0125. So now when we plug in our diameter into our energy balance, the friction factor from our energy balance gives us 0.007, which is not equal to what our Moody chart gave us of 0.0125. So we know that the diameter of 0.4 is not correct. So we need to move down from the value in our Moody chart to match up with the one from our energy balance. So I'm going to guess a higher Reynolds number, and so maybe a higher diameter. So because we have this diameter to the 5th power, very small changes are going to have drastic effects. So for my next trial, I'm just going to guess 0.41 feet, and I'll show you why. When you do 0.41, I get a Reynolds number that's equivalent to 6.88 times 10 to the 5th. Now, epsilon over the diameter changes to 1.22 times 10 to the minus 6. So as we would expect, the friction factor on trial 2 is equal to 0.0125. Now, I'm using the exact same value because really, this doesn't change how we read our Moody chart. But what does change is that when we use this in our energy balance, we get a friction factor of 0.0125, which is awfully close to what we're reading in our Moody chart. So although I've shown only, let's say, 2 iterations, you can get drastically caught up on this if you are reading onto the chart, make small changes as you go along. So a 5-inch diameter pipe would be most appropriate for our design of our case. In another screencast, I'll show you the super shortcut method, which will take all of the data and work we've already done, but use a computer solver to do all our work for us and give us the value quickly.